Well, good morning, everyone. This is Rick Hartung. I'm with Process and Safety Solutions. Hopefully everybody is doing well. Today's webinar is relief systems, and I know that this topic can be very overwhelming. And what we're trying to do and what I'm going to try to do today is kind of simplify some of the concepts. Now, certainly I will not be able to go into everybody's system to be able to help you to design your relief system, but I'm going to point out some specific points that you need to consider when you're looking at your relief systems in general. So what we're referring to mainly here and what we're going to discuss throughout this webinar today is that information that must be in your process safety information from a PSM standpoint. And one of those items within the process safety information is release system design and design basis. And if you notice, there's two parts to this, design and the design basis. And that's one of the things that we're going to spend a lot of time talking about today. So I'm going to give you and start out with kind of a brief overview what a relief system is. A relief system includes a relief device, and we're going to be talking about some of the more common devices today. It can also include a common vent or a header system. Those relief valves relieve either directly to atmosphere, or they may go into a common vent that is vented to atmosphere, or they may go into a header system and then somewhere else from there. It could also include a flare. It could also include a boiler. And I know most of you right now are saying, what do you mean a boiler? A flare is a device that essentially destructs or burns hydrocarbons, et cetera, that are relieved to some system. It could be to a knockout drum or to a header or somewhere else. And then the flare essentially burns that or destroys it. Boilers can do that same thing. You can put this relief materials into a stored area and then burn it to destroy it as well. It can also be a scrubber or an emergency dump tank. So maybe you scrub the toxics out before they're released to atmosphere. That's relieving to some type of a device, what we'll call a scrubber. It can be a dump tank. What we mean by a dump tank is maybe you have a toxic that relieves into another tank, and then that material absorbed into some type of solvent, so that you're not relieving the toxic to the atmosphere or the relieving media to the atmosphere directly. All relief systems have a design basis, and they also have an actual design. So in order to get to the design, we need to understand the basis. It is not as simple as just knowing the system pressure and slapping a relief device on it. Unfortunately, we see a lot of those in our compliance audits, and those are the things that we're trying to avoid, because certainly any pressure relieving device is going to keep you from a catastrophic event. Those catastrophic events can vary depending on what's in the vessel. If we're relieving liquids, for example, the severity may not be as high if you're relieving a gas or a vapor. We know what happens when you explode a tire, for example, that's filled with gas. That can be fairly catastrophic an explosion. On the other hand, if that same tire was filled with water and the tire fails, you may just get wet, and that's only. So let's talk about design basis. And I know that some here may be in the ammonia refrigeration industry or some other industry, and not specifically in an industry that has oil and gas, but the API codes and standards essentially refer to most of that as well. So even relief devices that are designed in the ammonia refrigeration industry have the API codes and standards, and some of those calculations contained within them. So it's not like that we can be divorced or removed from API standards. In fact, most of the API standards have some really good information, no matter what industry that you're in, to help you size the different scenarios that you may have in your facility. Keep in mind, API has as many as 14 different scenarios and relief scenarios that must, and the point is they must be looked at. They must be determined and evaluated whether or not those scenarios exist in your facility. We're all probably familiar with scenarios such as fire, the fire case, blocked outlet case, loss of cooling, thermal expansion, reactions, whether those are exothermics, runaway, etc. The list kind of goes on, but every one of those scenarios that are listed in API 524 must be addressed specifically, and that those must be documented as to how you address them and what was the outcome of that evaluation. Other considerations must be the material phase, whether it's a liquid, gas, vapor, or it's a combination thereof. So all of that must be documented. We know that, and we should know that a relief valve will respond, or capacities is different given what media is flowing through it, if it's gas or liquid. We must evaluate any auto refrigeration effects. For example, if you're relieving propane, we know that that pressure drop is going to create issues with icing downstream, perhaps, or other situations, depending on where it's relieving to. We must look at the device back pressure. Back pressure, we're going to spend some time looking at back pressure and what that means today. Oftentimes, this is something that's often overlooked, and that's a big mistake. Relief requirements, as we said, are not always simple. There's a lot of tools that can help us in designing and coming up with the relief scenario. There's tools like ProMax out there that you can use that help you model the various relief scenarios. There's HISYS out there that can be used. Even some relief vendors, relief valve vendors, can help you with the sizing process once you've provided them the information on what your requirements are. Remember that trash in and trash out. And what we mean by that, if you're given bad information in the sizing, obviously what comes out of that sizing exercise is going to be bad information as well. So making sure that all the information that you gather, all of the information that goes into sizing that relief device should be current and accurate as well. Sorry, trying to get to the other slide here. So, other things to consider in addition to that, to two-phase flow, auto refrigeration, and system back pressure is the excessive inlet pressure drops. Looking at your pressure drops to make sure that those are well below the 3% of the set pressure. So if you have 100 PSIG set on your relief valve, your inlet pressure drop shouldn't be no more than 3 pounds of pressure. More than that, then you could have valve chatter, and hopefully we'll understand what we mean by valve chatter later on when we look at the valve types and how they're designed. How about excessive pressure drops on the outlet? So the outlet of the valve to whatever device you have, whether it's to atmosphere, whether it's to one of those other devices, a dump tank, a flare, etc., those pressure drops must be evaluated as well. Typically, you want those pressure drops to be 10 to 15%, no more than that, certainly. But in any case, you must evaluate those pressure drops and to see what they are, because they are going to affect the valve performance and also could result in damage. Again, chatter, where chatter is essentially that valve opening and closing very rapidly. The other thing that we want to look at is vessel overpressures. We know that you have an MAWP for a vessel that overpressure can be as high as 121% in a fire case, 110% of the pressure in the case of a normal relieving event, and then other overpressures exist. And we're going to look at some of those depending on what you have and depending on your design of your system. We must make the proper selection of the relief device. And the proper selection really has to do with a lot of these things that we've already talked about. We've talked about overpressures, we talked about back pressures, etc. And we're going to talk about some of those issues right now. So we're going to look at 3 different types of relief devices today. I know there's others out there, but we're going to look at just the more common relief devices. First is the relief valves that are recoverable. And what I mean by recoverable, they open and they close. And those are conventional. And what we mean by that is it's just a spring-loaded valve and nothing fancy. We see spring-loaded valves in just about everything. Even your hot water heaters at home and in your house are spring-loaded type of valves. They are what we would call a conventional spring-loaded valve. The next type we're going to look at is a balanced piston or bellows type valve. We're going to talk about those as well. And then the last one we'll talk about is piloted type relief valves. They all have good applications. In some areas that we can use them, some areas we shouldn't be using them, yet we see them used all the time. Then we have the rupture disc. It's non-recoverable. The disc ruptures, it doesn't stop the flow. You're going to have to stop the process and replace the rupture disc when it blows, when it's by itself. And we're going to talk about a combination here at last part as well. Then you have the fuse plug. It's non-recoverable as well. And then you have a combination. You could have a relief valve and a disc, and we're going to talk about that one as well. So let's talk about the conventional valve real quick. So understanding how these valves work is pretty important. So I'm going to turn this on just a little bit. I'm doing a little bit of annotating on this and draw so we can kind of see what's going on here. So you have the inlet coming in, and then of course we have the outlet. So this is where the vessel may be connected here, and then it's going to overpressure and relieve out here. This is the valve seat. So this is what is actually lift. And then of course, this is the spring. So as the pressure builds up inside the vessel, it lifts the valve or lifts off the seat, and then it relieves the pressure this way. So we know that if we remember our math, we know the F is equal to PA. So F being the force, and that's the force and the spring constant. Pressure is what's actually in the vessel, and the area is this area right here under that seat. That force in that area is what, or that pressure in that area will have to overcome the spring force in order to lift. So conventional valves, the pros of the valve seat is, as a lower cost. The valve itself is a lower cost. It's a good choice if you're discharging directly to atmosphere. And we're going to explain why that's a good choice here shortly. The cons are the spring must be adjusted when there's a constant back pressure. And what we mean by that is that there's a pressure back here that's constant, that's pushing down on this valve right here. So because it's pushing down, it's going to keep that valve from lifting as it should. Now, if it's a constant back pressure, in other words, P equals C, a constant, then we know that we can adjust that spring such that the pressure in here is going to lift at the set pressure every time. On the other hand, when P is not equal to C, then we know that we can adjust that spring accordingly, depending on what that back pressure really is. A spring-loaded or conventional should never be used where the back pressure is variable. And we're going to explain that here in a second if you didn't understand what we did there already. Low relieving back pressure is allowed, so you can have some back pressure. Remember, I said this back pressure should be anywhere from 10 to 15%, but must be evaluated. And overpressure is required to fully open this valve. So what we mean by that is essentially that we need to have more than MAWP here to fully open this valve. So if we've got 110%, it means I need 110% open this valve enough or fully to relieve the pressure so that my MAWP never exceeds 110% of the pressure. So let's now look at, let me clear this first. If I can here, clear that. So now we're going to look at a balanced piston or bellows type. So when you have a balanced piston or bellows type valve, essentially what is different here is you have essentially a bellows covering this part of the valve, such that the pressure pushing up on this is the same as the pressure pushing down, so that it cancels each other out. So that now doesn't really matter if my back pressure here is constant or not. This valve is still going to perform and lift at the set point that we've decided with the spring. So we know that with the bellows, because we've isolated this area so that the area here is equal to the area here, then we're fine. Those actually again balance out. So again, if the back pressure was, say, 5 pounds of pressure, that really does not affect whether or not this valve is going to lift at set pressure or not. On the other hand, we can have too much back pressure, and we're going to be talking about that here in a little bit with these type of valves as well. And just so you know, when we get to the end of this webinar, if you've already written a question up, I'll answer those when we get there, even if we have to come back a little bit, okay? So the pros of a balanced or piston type bellows valve is the spring does not need adjustment when the back pressures change. It's a good choice where the back pressure is variable. It changes somewhat. It's not constant. They are at somewhat higher cost, and you do have somewhat better relieving, somewhat higher allowable relieving back pressure, but it's still restricted. Overpressure is still needed to fully open the valve. So then we come to the pilot controlled valve. So essentially what we have here is let me get my drawing up here again. So what we have here is the pilot. So the pressure comes into here, and now it'll lift this valve and whatever we set it for, and it'll determine whether or not how much pressure is on the back side of this valve, or on the piston, if you will. So if I remove all the pressure from this piston here, and it becomes 0, now that whole piston will lift up. This controls how much pressure is put on that piston and how tight the seat is as well. So now in this particular case, I don't necessarily care how much back pressure I have. Well, I do. I'm limited on back pressure to a certain degree, but from the standpoint of whether it's variable or not, it really doesn't matter. I'm going to lift this valve when it's required to be lifted, no matter what. And I can open this valve. I don't require the overpressure so much anymore either to lift the valve, because now I can control it all right here. So again, pilot is a great choice of valves. Again, I control everything here, and I can remove all of the pressure on here to open that valve fully. Even if the set pressure is 100 pounds, I could have that valve lifting full open rather than relying on back pressure. It's a good choice again where back pressure is variable. As we said, the valve is not depending on overpressure to open. They are at higher cost, and of course, material construction can drive some of that cost as well. Then you can have a combination of relief valves, and in this particular case, we've got a sorry, got ahead of it myself. So in this particular case, I'm going to turn my annotation on here just a second again. So in this particular case, we've got the rupture disc that sits here, and then we've got the conventional relief valve here. So in this particular case, everything, all the media is pushing up against this rupture disc. The rupture disc fails. Now the relief valve will be taking over. So in this particular case, why would we do this? For example, if I have something that's very corrosive here, then if it's very corrosive, then I would have to make sure that this the materials construction of this conventional valve were such that they could handle that corrosive environment. On the other hand, if I put a rupture disc here, then I can make this a carbon steel valve and then put exotic stainless or Hastelloy or whatever on the rupture disc itself, reducing my cost somewhat. So the cons are you still have to monitor this space in between here. And this is something we see quite often, where if you've got a space right in here, you got area that if this rupture disc here was just to leak by just a little bit, that the pressure comes in here. So now essentially you have pressure pushing down on this device and you have pressure pushing up. So essentially this disc may not work. If that leak is small enough, that disc may never lift, and therefore you would have no protection on your for your vessel at all. So you must monitor the pressure in that annulus between the rupture disc and the relief device. So let's talk about the two different back pressures. You've heard me talk quite a bit about back pressure in general, and this is one area that we see quite often that is not addressed appropriately or correctly. So we're going to talk a little bit about that, or spend a little bit of time talking about that today, just so that we make sure that when in your design of your systems that you're addressing back pressure. So the two back pressures we're talking about is superimposed and built up relieving back pressure. So superimposed back pressure is the back pressure that your relief device may see all of the time. So for example, if I'm relieving into a dump tank, or I'm relieving into a flare, or I'm relieving into another vessel, or I'm relieving into a header, that header may see back pressure all the time. Maybe that back pressure is only 3 pounds, or maybe it's 5 pounds, et cetera. And there can be different reasons for different pressures here. So keep in mind, if that pressure here is 5 pounds, and if we haven't adjusted the spring, so if I've got a 100 PSI G set, and I have 5 pounds of back pressure on here with no adjustment in the spring to compensate for that, this vessel now will not relieve until 105 pounds, okay? So back pressure affected when that valve can lift. That would be a violation. So a code violation if the valve was not designed such that would not relieve at MAWP. So if the MAWP is 100, that valve must be designed to lift at no greater than the MAWP. So that's why understanding what your back pressure and what the superimposed back pressure really is. It typically, again, comes from vents, header system tanks, vessels, and other relief devices as well. So if you have your system headered together, so you have more than one relief valve relieving into the same header, that one is relieving, the other could be affected by the back pressure and not relieve as well. The second thing we talk about, the other type of back pressure, is built up or relieving back pressure. And essentially that's the pressure as this relief valve is relieving. There is going to be some pressure drop or some delta P as a result of that relieving. So that's pressure drop in my line. That's even if I'm going to atmosphere, there's a built up back pressure that's occurring. So if I have a relief valve with an outlet of let's say 1/4 or 1/2 inch, let's make it a little bit bigger. Say I have a relief valve with an outlet connection of 1 inch, and that's a relief valve outlet connection. And I'm going 50 feet in a line that's 1 inch in diameter, there's going to be significant pressure drop in that line for that 50 feet. That is built up back pressure, and that built up back pressure has limits as well. And those limits we have to address as part of our design problem as well. So keep in mind 2 back pressures. One is the back pressure from other devices and other things like vents, from your headers, from your your knockout drum, or even from your flare system, etc. So these are some of the ASME requirements for sizing. And this is process only. So your steam requirements and steam systems, et cetera, state may require those be a little bit different, but they're not too much. For example, maximum allowable is 103 versus 105, et cetera. So you make sure that when you're looking at this table, that you understand that this is for process only, not for steam. So the first relief valve must be set at or below MAWP, or the maximum allowable working pressure. Overpressure, again, the overpressure is what we need to lift that a conventional valve, cannot exceed 110% on a single valve in a normal relieving situation. For overpressure for a fire case, it can be as high as 121% of set. If you have multiple relief valves, in other words, more than one, and a lot of steam systems, for example, have more than one relief valve that are required by code, you can have up to 116% of set. If you have a combination of rupture disc and a relief valve, there's a 10% penalty for that rupture disc in your sizing or your capacity of that relief device. And you must have some type of pressure monitoring, as we discussed earlier, in front of that PSV or downstream of that rupture disc. And again, keep in mind, steam requirements are going to be a little bit different. So this table, as you see to your right, is only in the case of process. So here are some typical violations that we see. Well, we've done many PSM compliance audits, and we look into relief systems. These are the most typical ones we see. And these are also the ones we see quite often that OSHA is citing. Now, OSHA doesn't cite as many as they used to, mainly because they don't have as many engineering folks at OSHA as they used to, and people that understand relieving systems. But I think that's changing with some of the recent hires they made to their staff. So here are the typical violations we see, and these are general, okay? General meaning these are kind of in all industries. So it doesn't matter what industry you're in, these are the violations that we might see. The design basis is not complete or documented. So if you don't have a design basis, how in the world do we know what your design of your relief valve was based on? Second is the basis does not match the design. For example, you might have said the basis was a fire case at 20,000 pounds an hour, but your relief valve is only sized for 15,000 pounds an hour, et cetera. So that would be a case where the basis does not match the design. Set pressures can be different. Also, back pressures can be different. For example, you actually did the calculation for back pressure and you had a superimposed back pressure of 10, but the relief valve was not sizing, and set pressure was not adjusted to match that back pressure. Also, set point was greater than the MAWP. Remember, we said if you have a single relief valve, that must be set at no higher than the MAWP of the vessel. Failure to consider all relief scenarios. Remember, I said when we first started this discussion that you must document all and evaluate all relief scenarios that are potentially there. 24 of them for a matter. Most of them you can go through fairly quickly and say they don't apply. But typically 2 to 3 of them apply in almost every situation. Fire case, blocked in case, loss of cooling case, et cetera. There are numbers that apply in just about all situations that you must look at and evaluate. So you may have 3 scenarios that apply. You must document what are the relieving scenarios for each of those. For example, you may have a relieving scenario on a blocked in case at 20,000 pounds an hour and the fire case at 15,000 pounds an hour. We need to document what the scenario and the results were for each of those. Again, failure to document all relief scenarios that were evaluated, and that's important. We're going to discuss why that's important here in a second. Device not sized to the worst case relief scenario. Like I said, gave you an example a few minutes ago. We looked at relief scenarios. We had 15,000 pounds an hour for the fire case, and we had 20,000 pounds an hour for the blocked-in case. But the relief valve was sized for the fire case and not the blocked-in case. We see that quite often as well. Others is you fail to consider two-phase flow. In this particular case that we're talking about is 20,000 pounds an hour was all liquid because it was a blocked-in case, where the fire case was all vapor. So failure to look at what was actually being relieved was even worse from that perspective. You need to make sure that you understand what the media is that's going to be going through that relief valve for each scenario. Failure to evaluate inlet pressure drops, must evaluate it regardless. Failure to evaluate outlet pressure drop, must look at it to see whether or not that becomes an issue in relieving properly or not. Here are some of the things for ammonia refrigeration. I know we have some refrigeration folks on here today, so I want to just go through some of these. And some of these are somewhat laughable. You relieve into another vessel. All well and good, but the relief valve was not sized to that. For example, the relief valve is a conventional relief valve, and when you relieve into another vessel, that conventional relief valve will have back pressure that can be varied. So as a result, that relief valve is not going to relieve at set pressure anymore. Headered systems have variable back pressure. We see this quite often where you have multiple relief valves relieving into the header, but there was no consideration given for the fact that you could have multiple relief valves relieving at the same time, affecting how other relief valves in that system can relieve as well. Fire case is not evaluated. For example, if you look at this picture to your right, there are 3 vessels sitting there. All 3 vessels could be subject to a fire. So now we have 3 vessels that are relieving essentially as that fire has taken place. Now we know for the most part in a fire case, the relief valve will open and close as that pressure builds and et cetera. So not all of them may simultaneously be relieving at the same time, but you could have 2 of them relieving. Well, when the other one built enough pressure, there's going to be back pressure on that relief valve, not allowing that relief valve to lift as it should at the right pressure as well. So making sure you evaluate fire cases and what's going to be relieving at the same time so that you make sure you're taking into account any back pressure situations. Liquid or oil relieves to the headered system. Well, I shouldn't have to explain the reasons why for this. For example, if you have oil relieving into your relief header, then since oil is not going to evaporate off, it's just going to sit in there, it's going to affect the performance of any relief valve downstream of that, and eventually you could affect all relief valves if it's going into a headered system. So oil, things like that should not be going into the headered system. They should be going in other places such that you're not affecting the performance of those relief valves that are in there, even if you have drains in there. So typically drains get open very frequently, and you could have a number of feet of liquid sitting on top of that relief valve, rendering it inoperable as a result. Also in the ammonia refrigeration, we see the incorrect use of the back pressure equations. If you look at IAR2, for example, there is an equation in there used for non-choke flow. And when you look at that equation, it's looking for equivalent length. That equation can only be used directly when the device is actually going to atmosphere. And then even then you have to look at that equation from the standpoint of, do you have any changes in diameters, et cetera? If some of those things are negligible, it might be okay to use, but keep in mind that if this is a headered system, that equation cannot be solved directly. It has to be iterated at the different points within the system itself. Oftentimes we'll look at ammonia refrigeration relief data and we'll see negative equivalent lengths. Well, if you have a negative equivalent length, I'm not sure how I can help you there. That's like having a negative volume. There's no such thing as a negative length. There's no such thing as negative volume. So we need to make sure we're looking at our results and making sure our results make sense. Can't have negative pressure drop either. You know, it's going to atmosphere. There has to be some pressure at the valve in order for you to have flow. And flow is not going to go from atmosphere back to the relief valve. So we need to make sure that, again, the results make sense. Incorrect outlet pressure, we're relieving to a header. So if we're relieving into a header, the outlet pressure when relieving into that header most likely is not going to be atmospheric. It has to be something other than that because there's many diameter changes of that header system before you get to atmosphere. Have to make sure that you're evaluating or using those equations based on choke flow or non-flow choke flow conditions. Can't use that equation if you have choke flow. So making sure that we're looking at those outcomes again to make sure that we're doing those correctly. And then use of the incorrect flow. Oftentimes we look at flow in a header based on the required flow rate of the relief valve. When you're looking at flow in a header, you must look at the relief capacity flow. So maybe the capacity of the relief valve is 100 pounds an hour and required is only 40 pounds per hour. A little bit oversized, I understand, but when you do your header calculation, it must be based on the 100 and not the 40. So making sure that you're sizing and understanding your back pressure correctly and sizing your header correctly is pretty important. So I've got a few items that I just want to kind of go over, and just so that we're all on the same page as some of these things that I'm talked about, and making sure that you're addressing in your relief design basis, et cetera. So in this particular case, I have, I'm trying to get my drawing up here. So in this particular case, I have 3 vessels. So these 3 relief valves are relieving into, this is a typical dump tank. So everything from these relief valves relieves into this tank full of water, and then it absorbed in the water and then comes out to the relief vent on the atmosphere. In this particular case, I've got 15 foot of water to the bottom of where the material from the reliefs is sparged into the water. So essentially what I've got is 6.5 pounds of back pressure on my system, 6.5 psig, especially if I put a constant purge in here to sweep this out, to make sure that I don't have dead legs, et cetera. So this 6.5 affects those relief devices. So rather than these relief valve lifting at 150 or 250, they're going to be 150 plus 6.5, unless that spring is adjusted. And that's what we should be doing, is adjusting that spring to take into account that back pressure that system would see. Typically, what we see in a lot of industries, it was never accounted for. So therefore, there would be out of compliance from a code perspective because the relief valve was not lifting at MAWP or less. Oops, sorry about that. The next one I want to kind of look at is why I said it was important to make sure we document all our relief scenarios. In this particular case, I've got a relief valve here lifting at 250. The MAWP, or the max MAWP, or the maximum pressure output of this pump, is 280 psig. So theoretically, I could be blocked in. No way to get out of that vessel, and this pump continues to pump. So in a particular fire case, if I had a fire under here, I would be sizing this relief valve for that fire case and that scenario. This would be relieving vapor or gas, right? Depending on what's in here, but for the most part, let's assume vapor in a fire case. Now, if I'm also going to look at this scenario blocked in, this is all liquid. So if I'm blocked in now, rather than vapor at that relief valve, I've got liquid, right? So I have two different potentials for phases. Both of those would have to be looked at specifically, and which one would be the one that I have to address. Now, if this 280 down here was not looked at, let's say, for example, and we see this quite often, original design, let's say, is 240. And if I looked at the scenario, and this was 240 PSIG, maximum pressure, then I would look at this and say, okay, the relief valve is set at 250, this is 240, so that scenario would not be a scenario that I would size this relief valve to. It would be some other scenario, because this pump could never cause that relief valve to lift. If I didn't document that, then at some point in time, just like in most processes, somebody comes along and says, hey, I need more production, so I'm going to increase the impeller size in this pump, or I'm going to replace that pump with something that gives me 280 PSIG, gives me more flow in there, therefore I get more production. If this relief valve now is still only sized for the vapor case, then because I didn't document that information originally, I couldn't go back and look at to see whether or not that would now be a scenario that would have to address. In most cases, it gets forgotten. So that is why it's so important that we document all of our scenarios, how that relief valve was sized, etc. And that way, if I want to ever make any changes to this system in the future, I can go look at that process safety information and make that determination as to whether or not I need to relook at resizing that valve or not, or the scenario is such that I can go to 280 and it's fine. So that's another scenario. Let me clear this. So let's go to the next one. Clear this off of here first. So the next scenario is we've got this vessel and this vessel all relieving into a headered system. And this is one we see quite often in the ammonia refrigeration industry and oil and gas industries, et cetera. So this one's a very frequent occurrence. So in this particular case, you can kind of see the design is relieving in the top of the header, et cetera, and that's fine. But this particular case, look at what's in here. So I'm relieving the shell, which contains oil, into this header. So if I ever relieve this, and this, let's say this was a heat exchanger, and that's what I think we've tried to say here, is this a heat exchanger? I relieve oil into this header. So now eventually, as that oil builds up in there, I start overflowing oil down to each one of these. Not to mention, this is already full of oil. So the more head pressure this builds, the less likely that relief valve will lift when it's required to lift. So therefore, let's never relieve liquids into a headered system unless that system is going to a knockout drum that knocks those liquids out. And even then, you must look at this portion of it here. Make sure that it's designed correctly. For example, if the relief valve was up here, then I would be less concerned about that material being left in here. So always look at the design to make sure that you're not creating a hazard as a result. So let's look at the next one here. This is, and I see this one, I'm sorry to say, we see this one way too often. So in this particular case, we have the relief valve that's relieving into another vessel. This is, again, fairly common in the ammonia refrigeration industry. So we've got an MAWP of 250 relieving into a tank that has a, let's say, an MAWP of 150. So I have a fire case, and I have a fire here. This pressure here is going to be 150, and this relief set at 250. So it's conventional relief valve. It's not going to lift until when? That. So 400 PSIG before this lifts, probably in the catastrophic range where we could see catastrophic failure of that valve. So making sure that we understand when to use the right valve. Now, perhaps if this was a bellows type valve here, rather than a conventional, that might work. On the other hand, a piloted valve might work as well. But in any case, a conventional without an adjustment in here would not work. You could put a conventional in here and set that conventional valve to relieve, rather than at 250, it relieves at 100, and that would work fine as well. So keep in mind that relieving into other vessels, you have to take into account the device that you're going to be using to make sure that that back pressure doesn't create a hazard as well. Clear this and go to the next one. I think I have one more or two more. Okay, in this particular case, I have a knockout drum. I've got the whoops, I'll go back here. Okay, I have a knockout drum. I have the knockout drum here, and then I'm going to a flare. And then I have some purge gas coming in here. And typically we see 5 to 10 PSIG in the purge gas. Essentially that purge is just a sweep of gas that goes through here, keeps the flare burning, et cetera, et cetera. It also keeps anything that's coming into that flare header swept out of there as well. So again, you have back pressure on each one of these valves, et cetera, back pressure here on each of those. So making sure that we're taking into account each of those back pressures here, especially if that's somewhat variable, then you need to take into that account. Conventional relief valves may work fine here because everything is set at 250 and we've got a constant back pressure. If that pressure is constant, then we can adjust the springs accordingly. So I try to cover most of the scenarios that we see in terms of sizing and back pressures and errors that are typically made. One of the things to keep in mind is always evaluate all possible relief scenarios and document regardless if not credible at the time or not. Remember, it may not be credible, like we talked about the blocked in case, or the pump feeding it may not overcome that for now at this present time, but by documenting it, we have that information in the future should we make any changes to the system then. Determine if you have single phase or two phase, any flashing effects when relieving. All of that goes and is important in sizing the relief valve at the end. Determine back pressures, constant or variable, making sure you understand the effects on the different device that you're choosing to do your relief, making sure that if it's constant, that the relief valve is adjusted for that. If it's variable, maybe you need to select a different type of valve to do the relief. Evaluate your inlet and outlet pressure drops based on the valve capacity, not the required flow rates, as we said earlier. Remember to evaluate overpressures and ensure they are within the rega gap requirements. Remember, I gave you a chart, the SME requirements for overpressures that cannot exceed 116, 121, 110%, making sure that you understand the code and standard that you're using and applying, and then use it correctly. Ensure that when using a single relief device, its relieving set pressure is set less than or equal to the MAWP, and that should be a THAN rather than EN. Ensure that at least one relief device, if more than one, is set at or below the MAWP. So with that, I can take some questions now.